Section 6 here, we're going to get into Lewis diagrams, and I will point out that I've heard these called Lewis diagrams, Lewis models, Lewis structures, Lewis dot models, Lewis dot structures, Lewis molecular models, just all sorts of different names. The big thing is the dot ones that are only dots are almost always Lewis dot models, dot diagrams, dot structures. You don't tend to hear the dot mentioned in here, even though some of them do have the dots in there, but those dots and these models are used to represent the sharing of electrons. Gilbert Lewis was an American chemist who was almost literally forced into exile. He was so rejected by the chemistry community. He is probably the man most deserving of the Nobel Prize in Chemistry to never get it, because he was just way ahead of his time. And it turns out he was right about so many things, but no one believed him at the time. And it turns out that his way of handling a lot of things was just the best, the simplest, the most logical. It just made sense. Anyway, I will point out that down here, what they call molecular models, I've always heard called space-filling models. And beyond that, I am not going to be picky about the names of the different types of representations here. But we're going to get into how you draw them. I will say that we tend to do these, as we start out here, with covalent bonding, where atoms are sharing electrons. And so the sharing of electrons fills up their outer energy level, obeying the octet rule, and so then we get that. So I'm going to skip over the slide. I'd encourage you to pause it, jot down the information on it, but I think it makes more sense to describe that in a diagram here. We have hydrogen. Hydrogen has one valence electron, and we've mentioned previously that is normally drawn on top, but we can draw it anywhere around it, and they know where this is going, that we're going to end up with a shared model here, so they started out by putting them on the sides here. Well, what happens is these protons are attracting these electrons here, but if the atoms get close enough together, then the protons also begin to attract the neighbor's electrons. And so the protons here are attracting these electrons, and the protons here are attracting these electrons, and it pulls them together to the point where they end up sharing that pair of electrons. The electrons literally spin sometime around one hydrogen and sometime around the other hydrogen, and sometimes one of them has both and the other one has none. Other times they each have one. They're sharing them. They both get them. Now, there is actually this tug of war, because then what happens is the electrons get too close to one another. They want to repel. If you keep trying to squish these two together, the protons are going to start to repel one another. And so then it turns out that there's kind of an ideal distance there. But this, H2, is more stable than individual H's. And so hydrogen is one of a handful of elements that never exist on its own in nature. It's always bonded to something else, or bonded to itself as in the form of H2. And so we can represent these with Lewis models, Lewis structures, whatever you want to call them, where the valence electrons give full octets, that is 8 valence electrons, although with hydrogen it only needs 2. I'd still call that a full octet myself. It's a full outer shell. To me, the octet rule is having a full outer shell. Normally that is 8 in the outer shell. Hydrogen is your major exception. This statement here is similar to something that I've said previously, that the number of electrons that it's going to share is equal to the number of electrons it needs. The other way to think of that is if you have a symbol here and it has, say, 5 valence electrons here, well then it needs 3, and so it's going to end up sharing 3. But the way that I describe that is that each unpaired electron becomes half of a shared pair. And so each unpaired electron becomes half of a shared pair. And so this one is going to end up sharing 3 pairs of electrons. And the non-bonding electrons are called lone pairs. The bonding electrons are called bonding pairs, or as I just mentioned, shared pairs. I've also heard these called unshared pairs. Those of you who have me live, remind me to explain that a little bit more detailed with the models I have in my room. Anyway, moving on. Here, fluorine, as a halogen, has 7 valence electrons, so we start with 7 dots around it. Now, you'll notice that they started in a location that would put a gap there and would put a gap there, so that when these two came together, they then have a shared pair of electrons. And that's how we do that. The other way that we can draw this is we can draw the line in there in place of the bonding pair or shared pair of electrons. We still have to have the unshared pairs around that one. And then this here is just the formula way of writing it. And then this one here is a space filling model of it. Fluorine is one of a handful of elements that always exist bonded to itself, like the hydrogen. There are actually 7 of them that exist as diatomic. Diatomic here meaning 2 atoms. And so those are hydrogen, and then nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Theoretically, underneath iodine, getting into astatine and the man-made 110 they probably do as well, but both because they're super rare, radioactive, one of them's man-made, we just don't know for certain, and it's not worth worrying about. I will point out that they make the shape of a 7 on the periodic table, and then you just have to remember the hydrogen in addition to that. There's 7 of them, but the fluorine there gets used on both legs of the 7 there, so it ends up only being 6 over here, plus the 1 from the hydrogen. I will also point out that in this region here, underneath of nitrogen, oxygen, and as we look at the other nonmetals, that many of them end up bonded to themselves. They just don't end up as diatomic. Phosphorus is almost always P4. Sulfur is almost always S8. There are other versions of sulfur out there. Arsenic is AS4, I believe. Selenium also bonds to itself, but I think we're getting into the metalloid region there, and so that may not be the case. When it comes to drawing loose structures, and I probably should have erased their work on this one and just worked it out by scratch here with my pen, but when it comes to it, start by drawing the Lewis dot model for each individual piece. My recommendation would actually be to go through the route and draw all 4 hydrogens. Now, because I know where this is going, I would draw them like that myself, but it's totally fine if you draw them all with the dot on top or on the left. It doesn't matter, because you're going to be rearranging them anyway. From there, the thing that goes in the center, and that's sometimes the hardest thing to decide, it's never a halogen, and it's never hydrogen, and that's because both of those only need one. It's frequently carbon, if carbon is around. It is always the element that needs the most. Valence electrons. And so carbon's going to go in the center, and then we're going to draw hydrogens around it, and I'm going to use their carbon and then just draw my hydrogens around it. So 1, 2, 3, 4, and then each one of those brought in 1 valence electron. So there we go. And it looks like that. If we want to turn it into this kind of model, then any shared pair of electrons just gets replaced with a line. And if there's unshared pairs of electrons, they stay there. This one happens to have none. I will point out that when the elements are side by side, when you have a, you know what, we'll do this on the next slide. Symbol, the dots are always between them like that. The lines are between them like this. If the elements happen to be above or below one another, say like this, then the dots get turned so that they're between them, or like this. And it turns out that they can share more than one pair of electrons, actually what the next slide is going to get into, but here real quick you can see the unshared pairs of electrons staying on those central atoms here. Not to say that the outside atoms can't have unshared pairs of electrons, just that these are all compounds involving hydrogen, and hydrogen only needs those 2 valence electrons. And 2 ways to check your answer. 1, are all full? That is, do all of them have a full octet? Of course, hydrogen only needing 2. And 2, do you have the correct number of dots? because we can't just make up dots. Those dots come from the fact that these things had a certain number of valence electrons. Carbon started out with 4 valence electrons, and then we have hydrogens each having 1, and there's 4 of those. That gives us 8 dots total, so you're only allowed 8 dots. Nitrogen has 5 valence electrons, hydrogen has 1 valence electrons, and there's 3 of them, and so that's only 8 dots. Same thing over here on water. This one only has 8 dots. Again, you could have a model that has more than 8 dots, but the number of dots you have has to equal the number of dots you started with, which is part of why I recommend starting out by drawing each individual element. And like I said, I'd even take the time to do all of the elements and then rearrange them as necessary. From there, my recommendation is always to start by trying to build a model and try one pair of electrons, one shared pair of electrons. It's called a single bond. If that doesn't work, then start trying higher order bonds. That is a double bond, which will look like that between your symbols. And because it's symmetrical 2 by 2, it doesn't matter whether we're talking up and down or side by side. As a molecular model, as I'll call it, where we do the lines instead, it will look like that. Or a triple bond, where we have 3 shared pairs of electrons. And again, they can be oriented such that the dots look like just multiple pairs. Pairs look like colons. Of course, when they're above and below, those colons get turned sideways. The other way you can think about it is the spots on a die, actually. Your standard die has a side with 2, a side with 4, and a side with 6. And the 2's always done on a diagonal, but if you can imagine those being vertical, it's like the spots on a die, and so they rotate around like that, or like this when we're doing them. And we're going to see an example here of one that actually needs those higher order bonds. So they tell us to do carbon dioxide, and they tell us the central atom is carbon. I'll tell you, you could have figured that out because of it's the one that needs the most. I'll also say it's usually the one you have the fewest of. But anyway, CO2 here, start out by drawing the dot model for each of them. And I'm going to change pen colors here for them. Of course, there's no difference. It's just going to help you keep track of where my electron dots go. Oxygen has 6 valence electrons. I'm going to duplicate that, but again, I'm going to do a different color here. And then I'm going to rearrange these. So I'm going to start by putting the carbon in the center. And I'm going to put an oxygen on either side of it. And so we'll do the yellow one over here, and it had 6, so there we go. And then the blue one. 1, 2, 3, 4, 5, 6. And now we've got all the dots we started with, and we have them rearranged. We put the carbon in the center, but again, you could figure out that it was in the center. And we check them, and none of them are filled up right now. None of them are happy. Well, at this point, we can start rearranging electrons. And so when single bonds don't work, then we can go through and we can start trying double bonds. So we take any unpaired electron, and those unpaired electrons can become half of a shared pair of electrons. Now, the oxygen over on the left-hand side is good. It has 8 pairs of electrons because it gets to count not only the 2 unshared pairs, the 2 lone pairs that it has, unbonded pairs, as your textbook said, but also the shared pairs as part of it. Now, don't get the dots on my smiley face. They are confused with the electron dots. But the carbon isn't filled up yet, and the oxygen isn't filled up yet. So once again, we take unpaired electrons, and we make them half of a shared pair of electrons. And so now, both the oxygen over here and the carbon are all filled up because they all have 8 electrons that they get to call their own. Now, cleaning that up a little bit, I personally would do this. And then it doesn't really matter where you put the other dots. I'm going to put them actually out here at an angle, and we'll explain later on why I am doing that. It's another section here in this chapter. But you're going to end up with some kind of odd spacing if you do it at the right angles, like I talked about before, of doing them kind of on each side. Well, then since it only has two lone pairs, two unshared pairs, doesn't matter where you put those two. And then, of course, you have the shared pairs. There's going to be one that is a gap in there. As a molecular model with the lines in there, or a Lewis structure with the lines in there, it would look like this. And tell you what, I'll draw those dots at different angles here just to show you it doesn't matter which way you do them, where you put that gap. And you always leave the unshared pairs of electrons on there, and we're only replacing the shared pairs with the lines. Now, the text here doesn't give an example of one that's triple bonded, but we're almost done with this section, and I want to make sure that you see that one of those. So into one of those other diatomic molecules is actually triple bonded. Oxygen, O2, one of the diatomic molecules, is double bonded like the carbon dioxide. All the halogens and the hydrogen are all single bonded, but anyway, I'm not going to take the time to color code here just so we can go a little bit faster through this one here. But there we have nitrogen. There's two of them, so we're going to have that. And I think already you can see that there's no way we could just make two of them together work because we have that. And so, yes, they each have these one unpaired electrons out here, but they each have 6, but that's, of course, not enough. So we're going to try another shared pair of electrons. And that gets us closer, but doesn't quite get us there. And so then try one more here. And then that actually gets us there, a triple bond like that. Now cleaning it up, I'm going to put the unshared electrons on the side like that. And again, we'll get into why I would do that, how you can know to do that. I'm not going to judge you. I'm not going to grade you if you put the unshared dots in the wrong place, but it turns out properly they would be out there. Or again, doing the line thing, it would be like this. Looks like an equal sign with an extra line in there. But that's an example of one that is triple bonded. And you can have compounds with a mixture of bonds, acetylene, C2H2. It turns out the final thing, you got a single bond between the carbons and the hydrogens, but a triple bond between the two carbons. If you take the CHM-110, the OChem stuff, we'll get into a lot of hydrocarbons like that, and you'll see there's a huge mix of single, double, triple bonds there. There are some exceptions to the octet rule. We've already mentioned the hydrogen one. I don't even really think of that as an exception because that first energy level can only hold 2, and like I said, I don't think of it as the octet rule as needing 8 valence electrons. I think of the octet rule as needing a full outer shell. There are some exceptions to having a full outer shell. Some nonmetals, like those, can actually form compounds that have 10 or even 12. I don't know why they list sulfur here, again, because phosphorus, it turns out, does the same. Chlorine, bromine, iodine, they do the same thing, where they can have extra valence electrons around them. I will also say there are some, like beryllium and boron, that can actually have fewer and be exceptions to the octet that rule. Actually, nitrogen joins that list as well. And so there are exceptions. We're not going to test you over exceptions, but if you see an exception, you should be able to work with it and just understand that it is, knowing in the back of your head that these are some of the ones that can be exceptions will make life easier. Anyway, that finishes section 6.